Okay, so on to tangles. Tangles are a recent notion in graph theory and one of its deepest notions, I think. Something like, on the level of regularity and the regularity lemma, something like that. It's a much more abstract notion still, but it's quite exciting. So tangles are a bit like brambles. You know brambles already? So brambles are a collection of connected sets, pairwise touching, and it's not quite clear why one considers them until one proves this tree-width duality theorem which says that brambles, high-order brambles, are certificates for large tree width with a sharp bound. So brambles were sort of purpose-designed to fit tree decompositions. And the earlier idea and the more fundamental idea are tangles. They didn't quite work for tree decompositions. That's how brambles were born. But they persisted as the deeper and more fundamental notion. And indeed, tangles have been generalized from graph theory to all sorts of other things. So Kai knows about those, and you know about those. So, right, tangles exist and can be considered in data sets and all walks of life. There's a book about those, which I'm not going to advertise here, but just as an accidental remark, that's coming out this year with CUP, Cambridge University Press, about tangle applications. So this is about tangle theory and tangles in graphs only. Still, the idea of tangles is perhaps best described by looking not too closely at graphs, but just asking or looking at clusters in some large point sets, maybe vertices in a graph. So what would be a cluster in a graph? Well, it could be a vertex set of a complete subgraph, a very, very clustery. It could be a vertex set of a subdivided complete graph contained in our graph that is a little sparser, but still these these branch vertices hang together a lot. So they sort of form a cluster, and you could have minors, large complete graphs, or even just grids. They're all a bit cluster-like in the following sense. And the sense is that if you have a graph decomposition of low order, so sets A and B of vertices that cover the entire graph, there's no edge from A minus B to B minus A. That's the separation. And it has low order if the intersection of A and B is small. Right, and if you have such a low order separation in a graph, then any cluster that deserves its name, any of those things that I mentioned earlier, cannot be split roughly evenly left and right. If you take a complete subgraph, it has to be entirely on the right or entirely on the left. If you have a grid, for example, it could be, maybe it could have 2 or 3 vertices on the left and all the others on the right, but you can't cut a large grid in half, or even roughly in half, by a very small separator. So if you have a k by k grid with k 100 or something, and you're allowing separators of size at most 5 or something, then you can bite out maybe 1 or 2 vertices of a grid and have them on the wrong side, and everything else will be on that side. But that's just going back to these examples of clusters that I gave you. But the whole point is that you don't have to settle for a definition of cluster. You don't have to say we're talking about grids or grid minors or TKRs or whatever. but any cluster that deserves its name will, for any low-order separation of the graph, lie mostly on the right or mostly on the left. Otherwise, we could cut it in half by a small separator, and it wouldn't deserve to be called a cluster. Just like that. Right? So every cluster orients every low-order separation. And now comes an observation, and that is there are two fundamental theorems about all these types of clusters that I have mentioned in graph theory that work for all of them, and related ones as well. Those theorems are going to be called the Tree-of-Tangles Theorem and the tangle-tree duality theorem, and I'm going to prove both to you. But there was a time when tangles didn't exist, and they were proved, or variants of them were proved for the other types of clusters. And one could then observe that the proofs really only needed this property. They work for all the various kinds of clusters, like large grids or grid minors or something, but all they really used was that every low-order separation got an arrow. So it didn't matter how the arrow was defined as long as it came from some sort of cluster. And so now in mathematics, when we have this situation, we have this sort of playground freedom that we say, oh, well, we just make a new notion, right? So rather than considering all these various kinds of clusters, we make a definition, and we invent tangles. And what are tangles? Tangles are going to be orientation of sets of separations which I denote as SK. Those are all the separations of order less than k in G. And an orientation of a set of separations, like SK, is a way of putting an arrow on every element. Every low-order separation, every separation of order less than k, with fewer than k vertices here in the intersection, gets an arrow, that way or that way. That's an orientation of SK. And tangles are collections of these arrows, one for every low-order separation. So the whole graph could look more like this. So you might have a low-order separation here, and you might have another one there, and maybe a few more here. So a collection of arrows like this one here, induced, for example, by a large grid, which has only a few points on the wrong side of these separations, such a collection of arrow would be a tangle. A tangle, an orientation of SK, that would be a tangle of order k, or a k-tangle. Now that's a slightly unfortunate notation when you have something called a tangle of order k, you assume that there's a definition of tangle, there's a definition of order, and then you consider those that have order k. But that's not the case here. So there is no such thing as the order of a tangle. Right? Tangles come complete with this, in graph theory at least. So we have a tangle of order k that is an orientation of sk. And that's also called a k-tangle then. Now, is it any old orientation of sk? Well, no. If we wanted to reflect or to be the trace of these funny clusters that we can't sort of get a hold on, then, for example, orienting this separation to the top left and that one to the right would never be induced by any such green cluster, whatever definition you gave it. So a cluster will never lie both here and at the same time there, because the intersection of those sides is empty. Right, so it's not any old separation, but it's a consistent orientation. So a tangle of order k is a consistent orientation of sk. What is consistent? Well, consistent is induced by such a cluster, or oriented towards the cluster, not away from it. All right, so that's my definition of consistent. And my proposition now is to say, okay, let's forget about considering clusters in graph theory. Let's forget about talking about grid minors and TKRs and so on, and just talk about tangles, talk about consistent orientations of sk, and prove theorems about them. Anything wrong with that? Yes. There's something very, very wrong with that. And that is, it begs the question. Right? I've just defined consistent as oriented towards some cluster. I've used my vague notion of a cluster, whatever it may be, in order to define the orientations of sk that I'm talking about, which is not allowed if we then want to take the next step and say we forget about clusters and just talk about these consistent orientations, then we no longer know what consistent means. So the task is, or has been, to come up with a definition of consistency that works irrespective of anything cluster-like. Okay, and here's the definition. So, k-tangle. So, same thing as here. This is an announcement. This is the definition. A k-tangle is an orientation of sk, so all the separations of order k in the entire graph get oriented. What exactly is an orientation? Well, let's make it precise. So orientation, a separation is just a two-set of A and B like this, with no edge from A minus B to B minus A. That's a separation, right, by definition. And we can orient that by replacing this two-set with either of the two ordered pairs. Right? And choosing one of these ordered pairs is my formalization of putting a blue arrow on that separation. And which way does the arrow point? Towards the right-hand side. So the pair A comma B is my formal definition for the blue arrow pointing from A towards B. Right? The ordered pair B comma A would be the other arrow. Okay, but you don't, we have to make sure that we don't need the arrows in anything formal. So here's the formal definition of an orientation, either of two orientations of one separation, and orienting a whole set of separations means orienting each one of them. So an orientation of SK is a set of oriented separations that contains, for every unoriented separation in SK, exactly one of its two orientations. Okay, when is such an orientation of SK a tangle? If it avoids, has no subset in, that's a big T, that's not a chore. When I draw a little version of that, that's going to be a chore. So that's a big T. And that is the set of all triples, A1, B1, A2, B2, A3, B3. And when I say triple, I mean unoriented triple, just a three set, which may contain three elements, and may contain only two elements, or only one. So these three things needn't be distinct, right? So all three sets such that the union of the wrong sides, those away from the arrow, right, so the left sides are those that we don't point to. Makes up the entire graph. So that's forbidden, right? A tangle is an orientation of SK. So for every low order separation, you choose one of A comma B or B comma A. And whenever you look at most three of them, the union of the small sides, small, those that you're not pointing towards, must not be the entire G. So avoids translates to must not be equal to this. So that's our formalization of this consistency, which was informally defined earlier as pointing towards the cluster. There'll later be a formal notion, a formal definition of consistency, which is weaker than this. So this was only a term used for the introductory bit of this lecture. Don't write it down. Okay, so here, if you take any three separations as oriented by the blue arrows, there's lots that is not covered by the wrong sides. So all this green stuff here is not in either of these three wrong sides. If we had allowed this pair, then what is the wrong side of this red arrow? Well, it's everything here. What's the wrong side of this red arrow? It's everything here. So the union of those two is easily G. And that is forbidden in a tangle. So a tangle would be forbidden to contain these two orientations indicated by red arrows of separations, because that would be a 2 set with this property. That's forbidden. Okay. Good moment for a break and questions about the notion of tangles. Okay, then just one more observation. Every k-tangle tor induces an L-tangle for any L less than k. And what do I mean by induced? Well, I mean that this k-tangle is an orientation of Sk, and a subset of Sk, well, Sl is a subset of Sk. Right, the separations that have order less than L have order even less than k. So Sl is a subset of Sk, so when we have a tangle of Sk, then Sl gets automatically oriented. Right, and of course, you won't have a triple in here because you have a subset of your earlier tangle. So this would be simply the tangle tor intersect Sl with an arrow, by which when I put an arrow over a set of separations, I mean both orientations of any element of Sl are in this Sl arrow. Right, so that's something for later, that tangles induce lower tangles. And our aim in this group of lectures is to prove two theorems. One is the so-called Tree-of-Tangles Theorem, and that gives us something like the tree decomposition that we had for k-blocks. Do you remember that? I was sort of messing around in this corner here, getting all hung up about k being fixed or not fixed. Remember that? Right, so when we had k-blocks, I told you that for every k, there's a tree decomposition of the graph that distinguishes all the k-blocks in the sense that it has adhesion less than k, so all the adhesion sets have order less than k, all the separations induced by the tree decompositions have order less than k. So this k-block, which is an example of a cluster, has to lie entirely on one of the two sides, and the tree decomposition has this property that every k-block lies in one part, and distinct k-blocks lie in different parts, so it distinguishes the k-blocks in this sense. And we'll have a similar Tree-of-Tangles theorem for the genuine tangles. And now, of course, when we talk about a tree decomposition, such a tangle cannot live in cannot obviously live in a part. A part is a set of vertices, and a tangle doesn't have a set of vertices. A tangle is some orientation of some set of separations and so on. So we'll have to make precise what it means for it to live in a part of that tree decomposition. And you may be guessing it already. The definition is even simpler than the subset definition for k-blocks and parts is for tree decompositions, but we'll get there. That's one separation, one theorem. When you have lots of k-tangles, there's going to be a tree decomposition that distinguishes them all a bit like those k-blocks. And indeed, there is going to be one tree decomposition that distinguishes all the tangles, even of different orders, k-tangles, I-tangles, M-tangles, L-tangles, and so on, in this way, all simultaneously, unless they cannot be distinguished. And two tangles where one induces the other like this one cannot be distinguished. Well, and I haven't told you what distinguished means. It means the obvious thing, that there exists a separation that they orient differently. So if one tangle is a subset of another tangle, then obviously its elements, its oriented separations are elements of the other tangle. So it cannot, neither can orient any separation differently from the other, but that's the only exception. For any two tangles such that neither is a subset of the other, there is a separation which they orient differently, otherwise they would be the same tangle if they have the same order. No, not even then. If they don't contain each other and they're different, then such a separation exists, and the assertion will be that there will exist a tree decomposition whose induced separations, those at the adhesion sets, will suffice to distinguish any pair of distinguishable tangles, tangles that don't include each other. That's the Tree-of-Tangles theorem. Then there's a tangle-tree duality theorem, which is a bit like the tree with duality theorem, which tells us it gives us a tree structure of the graph if there is no k tangle at all for some given k, or no other type of tangle, as we'll get to later. So that's like brambles. If there is no large order bramble, then there exists a tree decomposition into small parts. Right? And this Tree-of-Tangles theorem, tangle-tree duality theorem says the same thing. If there isn't a large tangle, then there's a tree structure or a tree decomposition into something like small parts. So that's where we're heading. And today I'll give you two proofs of the Tree-of-Tangles theorem, two rather different proofs, and the first one today. And before that, we need a little more preparation, and I'll give you that now. Any questions about this? Okay. Okay, so the first thing is the notion of nestedness. You probably know it for sets. So two sets are nested if one is contained in the other. Okay, and we want a similar derived notion for separations. Unoriented separations. And basically, two separations are going to be called nested if we can choose a side in one and choose a side in the other, so that one of these is a subset of the other. And for the other two sides, then the same will be true with the inverse inclusion. Okay, so that's the motivation. So the picture that you should have in mind is that if you have two separations like this, so you have AB and CD, so A is this part, B is the entire right, C is the entire left here, and D is that little bit there, then those two separations would be nested because A is a subset of C and B is a superset of D. Right? Okay. So when are separations not nested? Well, the picture to remember there is this. So you have AB, left and right, and you have CD, or I usually have it the other way around. So C is up and D is down. So this little oval here is the intersection of C and D. This little oval there is the intersection of A and B. All right? And if there are vertices in all these four corners, then these two separations are not nested. So it's not possible to find one of those two and one of those two so that together they satisfy this. You can play with it and convince yourself that it isn't possible. Right? So these two cross. Cross is defined as are not nested. I haven't told you what nested means in any formal way just yet, but I will in a moment. But before that, we need a definition. So for oriented separations, let AB be bigger than CD if A is a subset of C and D is a superset of B. Right? So as I told you, the right-hand element of such an order pair is the one that we mean. That's where this separation points, right? So this points towards B, that points towards D. So this here includes the assertion that D is a superset of B, which corresponds to this bigger, right? If you don't know which way around it is, think of the right-hand sides. But it would not be enough for the definition to just say AB is at least CD if B is a superset of D. You can tell me that. It will be here forever, right? Just imagine they fail to wipe the board afterwards. It'll be here for centuries. So tell me of such errors. Right. So it would not be enough to just forget this condition and just require that. You can play with examples to see why. The reason is that the intersection can vary. So this can remain constant, and A and C can still vary if you allow the intersection to vary. If you have separations of order 0, then it's the same, right? So if you have bipartitions of the vertex set, then B is a superset of D, if and only if A is a subset of C. But otherwise, we need both. In general, we need both. Okay, so that's the definition of this partial ordering. It is indeed a partial ordering. So it's transitive because that thing is transitive. Well, because the set inclusion is transitive. And we need a little remark, and that is that, well, let me introduce this notation at the same time. So R arrow is one of the two orientations of the separation little r, whenever little r is a separation. So whenever R and S are separations, like these two, unoriented separations, then putting an arrow above them gives us oriented separations. These are orientations, A comma B or B comma A. And there's no default as to which arrow denotes which of the ordered pairs. Right? So if you just say, given a set, that is a separation, this set, for example, and if we call that little s, then little s has two orientations, the ordered pairs AB and BA, but we don't know whether little s forward is AB or whether little s forward is BA. Okay, so this is an arbitrary orientation of some separation R. This is an arbitrary orientation of some separation B. And when we have that, and we reverse the arrows, so we turn AB into BA, then partial ordering flips. So that's easy to check, but it's something that we use all the time. Okay, and now here's the definition for nested. Separations R, S are nested if they have comparable orientations. Right, so that's something like, this is a formalization of what I said earlier. It's possible to pick sides, one side in R, one side in S, so that there's an inclusion between the side we picked here and the side we picked there, and there's the reverse inclusion between the other two sides. Right, there are 8 cases or something if you write all that down explicitly, which is why this is a neater definition. So comparable refers to this here. Now let's just check. Why is the unoriented separation AB nested with the unoriented separation CD? Well, because there exist orientations for example, this one here, which would be that. Pointing towards this. And this would be that. There exist orientations that are comparable. Indeed, they are. They satisfy this. Okay? And I could have picked those orientations. Then this would have flipped. I could not, in order to prove to you that these two are nested, choose those orientations. Right? They're not comparable. This is not less than or bigger than that. Right? And similarly, I could not have used those. But those are a witness, and those are a witness to the nestedness of these unoriented separations. Okay, any questions? Good. Then we have the first lemma. And the first lemma is the fish lemma, just because I found that here when I came this morning. The fish lemma says that for any crossing separations R and S and any other separation T, we have that if T is nested with both R and S, then T is nested with every corner. And I haven't told you what corners are, but I will now. Or corner separation of R and S. That's the assertion. What's the corner separation? Well, it's what you expect. So here, you could, the upper right corner, what's the obvious separation? Well, it's the separation where this is one side, right? That's the intended corner. And that's the other side. Okay, so that's the separation, top right against the rest. So that's A union D, comma, C intersect B. Right, that is indeed a graph separation. You have to check that. Right? You have to prove that there's no edge from this minus this intersection here to that minus this intersection. But there isn't, because those two are graph separations. Okay, so those are corner separations. And the fish lemma now says that if we have two crossing separations, R and S, and we take any separation, any other separation T, that is nested with both R and S, then it's nested with all four corners. So here's a corner, this corner against the rest, that corner against the rest, and so on. That's the fish lemma. So let me prove that. Maybe I don't need to write very much. Yeah, I do need to write a little bit. So I want to keep the definition of nested, so we need this definition, but I'll make some space above. So one can really learn window cleaner skills doing maths lectures. Let's see. Okay. So our assumption is that T is nested with R and S. So that means that the assumption that T is nested with R means there exist orientations of T and R that are comparable. So there exists an orientation T of T that is in fact less than some orientation of R. Let's give that a name, R. So this comes first. If T and R have comparable orientations, so there's one orientation here, call it T prime, that is comparable to some orientation of R. If it's comparable by way of being bigger, well, then we just invert both orientations, and then the other orientation of this little t would be smaller than the other orientation of this little r. Right? So it doesn't entail any loss of generality to say there's an orientation that is even smaller, not just comparable, but smaller than some orientation of R. Once I've chosen this, I cannot, this will be fixed. Right? This depends on this here. Right, so we know that, and we know the same for S. Right, and now one wonders, can we choose the same orientation here in both statements or not? If we can, same orientation in both these, then we're done, because that's what this picture shows. There is one orientation here which is less than some orientation of R, namely this one here, and some orientation of S, namely that one here. And then it's easy to compute that this is nested with every corner. So for example, take the small side of T here, right? That is a subset of this corner separation that points to that corner against all the rest. This is a subset of this rest, right? This is also a subset of, if we take this corner, of that rest. And once more, it's a subset of, for this corner, this rest. And similarly, the right-hand side here is a superset of this corner, and of this corner. So how about this corner here? Well, that's the only non-trivial one. It's easy, but not, well, it's nearly non-trivial. So what about this? This is a subset of the wrong side of R and a subset of the wrong side of S. So it's a subset of the intersection of those two wrong sides. But the intersection of those two wrong sides is precisely this side of this corner. And similarly, that is a superset of the correct side of S and also of the correct side of R. Therefore, it's a superset of the union of those two correct sides. And the union of those two correct sides is precisely the right-hand side of this corner. Okay, so that's just stare at it, and that's easy. So what if not? Well, then we have this picture. Then we have T here, and this orientation is less than some orientation of R, and this orientation here is less than some orientation of S. Right? But then these two are nested. These two have comparable orientations, not the ones I drew. But you just flip one of them. So if you flip this one here, I want to show that this is greater than that one here. Why is that so? Well, how was it defined? It was defined as what T right is greater than. So T right is greater than R right. So R left is greater than T left. Right? We flip this when we reverse arrows. R right is greater than T left, which is greater than S left. Okay, so here we have a contradiction because we assume that R and S cross. And that's important to note that the fish lemma is actually not true for non-crossing separations. But we're not assuming anything about T. So T can be any separation. Okay, questions? No. Good. That's the fish lemma. Then one more, a few more properties. Submodularity. Sounds a bit terrifying. It's very simple. You don't, obviously there's a reason why it's called submodularity. You may have seen submodularity before in optimization or somewhere. And if you like, you can sort of find out, discover why what I'm going to tell you is called submodularity, but you don't have to. So it says that for every opposite corners, of R and S, two separations. I don't have to formally write crossing here, but that's the intention. We have the following inequality, in the opposite corners C and D of R and S. The orders of C and D sum to, at most, the orders of R and S. And in fact, if you do the sums, you'll find that there's equality here. Right? So it's just a calculation. You have the sum of the orders of R and S is you count all these vertices here, and you count all those vertices here, and you just sum them up. So those in the middle get counted twice. And when you sum opposite corners, say this one here, you count all those, and you count all those, and again, in the middle, those are counted twice. So in fact, we have equality here, but that doesn't have a name. Well, it does, but so this is the important inequality, and that's called submodularity. Now we need a couple of properties of tangles. The first property is consistency. Now, this is the formal consistency, which I mentioned earlier, not the one from the introduction, which was sort of in a circular way motivated or defined by clusters. So consistency, axis an orientation is called consistent if we don't have arrows pointing away from each other. So formally, whenever we have R bigger than S, so R would be this way, which is bigger than S that way, and S is in a tangle, then we can't have the inverse of R in the tangle as well. Okay, so maybe since I'm using notation anyway, I can just write this. Right? That would mean that Tor contained two oriented separations pointing away from each other, and that's not allowed. Then we have the profile property whenever you have in your tangle two separations. I drew them as crossing separations, but you don't need it formally. And you consider a corner, this one here, then this must not be oriented in this way. So you can write that down formally. If this is AB and this is CD, then this corner separation, this yellow one here, is A union C, comma, B intersect D, oriented that way, and you mustn't have the inverse orientation in the tangle. So the inverse orientation of this corner could be not in the tangle for two reasons. One could be that the other orientation is in the tangle. Remember, a tangle of SK, a K-tangle, contains exactly one orientation of every separation in SK. So if that orientation was an element of Tor, that would be a way to satisfy this property. Property P. But there's another way, and that is that this corner is not an SK, so the tangle doesn't have to bother with it at all. It doesn't orient it at all. So that's why I'm writing it in this convoluted negative way, that the wrong orientation is not in the tangle. I'm not asking that this orientation must be in the tangle. It can also fail to be in the tangle if this has order bigger than K, or at least K. That's the profile property, and it's easy to check the tangles do in fact have that. Right? Why? Because if this to the right is in the tangle, and this is in the tangle, and that was in the tangle, what would be the union of the three small sides? Would the entire left, union the entire bottom, union this little corner here. And that's the whole graph. Remember that all these intersections and these ovals are always contained in both. So tangles have this profile property, And tangles are not just any profiles, but they're robust profiles. And that is that if you have two separations and you're assuming only that one of them is in Tor, but you're now considering the two corners to which it points, then you must not have both these pointing the wrong way at once. Okay? So these are three, proof is the same thing, right? If this is in the tangle, then this is a small side. And if these two were in the tangle, then this corner would be a small side, and that corner would be a small side. And then all three small sides would make up the entire G. And that then wouldn't be a tangle. Okay. And now we need the definition of distinguish. So S distinguishes two tangles, Tor and Tor prime, or two orientations, if you like, of some, or two sets of oriented separations, it doesn't matter. It distinguishes them if, let me write, Tor of S is not equal to Tor prime of S, where Tor of S is the orientation of S, that's in Tor, and that's the orientation of S, that's in Tor prime. So S distinguishes them if the two tangles orient S differently. And it does so efficiently if it distinguishes them and no separation of smaller order than S does so. So it's the smallest, a separation of the smallest possible order to distinguish these two tangles. And that's all we need. And now we can have the theorem Tree-of-Tangles Theorem. Every graph G has a nested set of separations that distinguishes all its tangles. And by all its tangles, I mean all those pairs of tangles that can be distinguished at all, where we don't have one inducing the other. But they don't have to have the same order. Right? You could have a 7 tangle and a 10 tangle, and in your nested set of separations here that the theorem offers, you will find one separation that this 7 tangle and this 10 tangle orient differently, unless this is the one of them is a subset of the other, so that the 7 tangle is a subset of the 10 tangle. Okay. And for a proof, we need a little lemma. No. It's the Splinter Lemma. And the Splinter Lemma says, what you can read there, every splintering family, I'm going to tell you what it is, every splintering family of non-empty sets of separations has a nested family of representatives. So if we have a family of sets of separations, so what will those be later? AI will be all those, well, be some set of separations that distinguish the ith pair of distinguishable tangles. Right? We want one nested set of separations that distinguishes every two tangles that can be distinguished at all. So let's enumerate all these pairs of tangles that can be distinguished from 1 to n. Then we'll have sets of separations that distinguish them. For example, all of them. We'll later have a subset. Right? So the ith pair is distinguished by the separations that are elements of big AI. And the assertion of the Splinter Lemma is exactly what we want, that we can find representatives, one little AI in every big AI, that are nested. Right? And then every pair, the ith pair, will have a little AI in our nested family. So the little AI will distinguish the ith pair. So our collection of little AIs will serve as a witness to that theorem. Have you got that? Yeah? Okay, and now you need the definition of splintering to make that true, that we do have a nested set of representatives. And this notion of splintering somehow encodes all the proof arguments that were previously used in proofs of the Tree-of-Tangles theorem. So I'm going to show you a very short proof, and earlier proofs had all sorts of ideas that all went into this definition of splintering and the splintering lemma, and from that it'll be one line. Right? Okay, so a family of sets of separations, splinters, if whenever we have a little AI and a little aj, that each is not contained in the big A, I, or j of the other, and cross, then there's a corner of the two that is in one of the two, in either big AI or big aj. Okay? That's the definition of splinter. So let's prove the Splinter Lemma. We'll do induction on n. That starts at n equals 1, so if we have only one non-empty set of separations, then just pick any element, and that's a nested subset. Okay? So, induction step. By the induction hypothesis, there exists a family of choices, A1 to an-1, nested representatives of A1 to an-1, right? We'll just apply the induction hypothesis to the first n-1 sets. And we want to find a little n in big AN to add to this. We want the little an to be an element of big AN, so as to represent that big AN. And we want it to be nested, ideally, with all these. So if one of the AI here is already an element of AN, of big AN, we could choose that. Right? Because these are all nested with each other, so that little AI would be nested with all these. And if it's an AN, big AN, we choose it as the representative of big AN. So we may assume that for all I, we have AI is not in big AN, so it's in AI without AN. Right. Now we choose AN. How? In such a way that it crosses as few AI, I from 1 to n minus 1, as possible. Okay, and it doesn't matter whether when you're evaluating few, whether you count the separations or whether you count the indices I such that this AN crosses AI, right? One separation can be A7 and A3 at the same time, but it doesn't matter how you do the count. Okay, that's our choice for AN, and that is going to stay fixed until the end of the proof. Everything else will change. Right, so we choose that, and now claim for every I, the set AI prime those elements of AI that are nested with AN is not empty. Okay, so in every big AI, we look at those elements that happen to be nested with AN. So that's claim 1. Let's prove that. Fix I. We may assume that not only is AI not an AN, but also that AN is not an AI. Because if it was an AI, we'd be done. We would have shown it would be an element of AI prime, right? If little AN is an AI, it's certainly nested with AN, so it would be an AI prime, and that would conclude our proof that this is non-empty. And also, we'll log. Do you know we'll log? Without loss of generality. Right? Also, we'll log AI and AN cross. Why? Because otherwise, if they're nested, then AI, this little AI, would be nested with AN, and we would witness that this is non-empty. So we have little AN in here and little AI in there, and that's exactly what we need for splintering, right? For every crossing pair, and the two that we're considering are crossing. There's a corner C of AI, AN in AI or in AN. Right, and that's because our whole family splinters. Okay, but now let's look at this. We have AI and AN crossing. And now we have a corner that's in here. I would like that corner to be in AI, because we're looking for an element of AI that is nested with AN. And a corner of these two, any corner of those two, is nested with AN. So I would like the corner to be in big AI. So let's show that it can't be in AN. So what if the corner was in AN? Well, I claim that, well, we would let's not claim. If the corner is in AN, let's show that it violates the choice of little an. Remember, little an was chosen so as to cross as few AIs as possible. Let's call them AJs now because I is fixed. AN was chosen so as to cross as few AJs as possible. Now this little corner here doesn't cross AI, whereas AN does. So it's off to a good start as a candidate for being chosen as little an. So let's look at the other AJs and see how many AJs the C crosses compared with those that AN crosses. And now I claim that the C, the corner, crosses all those that cross AN. And then it's a really better choice because it also crosses AI. So why does the corner C cross all the, why is that nested with all the AJ that AN is nested with? And it's also nested with AI. Sorry, I say cross AI. So once more, we need to show, in order to see that the existence of little c violates the choice of AN, that it crosses more, that it's nested with more AJs than AN is nested with. And so since it's nested with AI, but AN isn't, all we need to show is that C is nested with any little AJ that AN is nested with, and more. So let's look at a little AJ that AN is nested with. Well, a little AJ that N is nested with, this AJ is also nested with AI, because all the little a's were nested by assumption. So this is nested with every corner, in particular with our corner. So tick. This corner cannot be an AN. That would violate the choice of little an. And so it must be in AI, and that's what we want. So let me, to make this clearer, say, nested with as many AI as possible, rather than cross as few as possible. Right. So that ends the proof of the claim 1. Now claim 2 is that A1 prime, A n minus 1 prime splinters. Okay, let's prove that. Prove that. Let's look at elements, a little ai prime in big ai prime without big aj prime. And little a j prime in big A minus a I prime. Right. Let's assume that they cross, and we have to find a corner that is either in ai prime or in aj prime. Now, we know that this little ai prime is not only in here, but it's even in ai prime minus the entire aj. Why? Because how does the entire aj differ from aj prime? Well, aj prime contains those of its elements that are nested with an. But little ai prime is nested with an, otherwise it wouldn't be an ai prime. So the only way it can be an aj, the entire aj, is by being an aj prime. So by deleting that prime there, we're not going to change that. So we have these more general properties as well. And so if we now just simply forget that these are in ai prime and aj prime, which are subsets of ai and aj, then we can use the splintering property of big ai and big aj that we have by assumption. ai prime and aj prime have a corner in ai or in aj. And we would like that corner to be in ai prime or in aj prime. But it is because we use the fish lemma with this as an. So an is nested with both these, so it's nested with every corner. So this corner is nested with an, and therefore also in the primes. And that's the end of claim 2. Now we need just one more line, proof of Splinter Lemma. By induction, applied to the AI prime, right? These are non-empty sets that splinter, right? A splinter. We apply the induction hypothesis to those. There exist representatives A1 double prime to a n minus 1 double prime of those. And we just append an to get our nested representatives for the original family, because all these are nested with an because they're in their respective AI primes. Okay, questions about the splinter lemma? No. Okay, thank you. Then let me prove the Tree-of-Tangles theorem. It will take 5 to 10 minutes. So I'm sorry I ran out of time, but it's not going to be long now. Proof. Enumerate pairs of distinguishable tangles 1 to n for the pairs, right? Let AI be the set of efficient distinguishers of the ith pair. Right, so AI is not empty. It contains different distinguishable tangles. Can have a distinguisher, and they even have one of smallest order, so that's an efficient one. They're non-empty. And all we need, as I pointed out earlier, is that this family splinters. Right, and then we have a nested set of representatives, and we can distinguish all the tangles by this nested set of separated representatives. So we have to show that it splinters. Let's consider two elements, T, efficiently the jth pair of tangles, Tor prime and Tor. Thank you for nearly mentioning it. And S in Si. And because we have to check splintering, we can immediately assume that this is not an AJ and this is not an AI. And this separates tangles, distinguishes tangles sigma and sigma prime. So this notation indicates that sigma orients S upwards and sigma prime orients it downwards, right? And Tor orients T to the right, and Tor prime orients it to the left. Okay, so let's look at we'll log S is at most T. order. Now let's look at this corner here, C. If this has order at most t, I claim that this lies in AJ, which would complete the proof of splintering. We want a corner of the two that lies in either AI or in AJ. So let me prove that. How does Tor orient? No, Tor is blue. How does this orient this corner? It must orient it that way, because Tor orients this t towards the right. Sorry. I have to say previously that Tor also orients S, because S has order at most t. Right, it orients it somehow, and I'm just calling I'm assuming that Tor orients it as sigma does. I could assume that it orients it as sigma prime does, but now let's assume that Tor orients S as sigma does, and that's how C is defined. So C is the corner where Tor orients both S and T. And then it also has to orient this corner if it has the right order, and by the profile property, it can't orient it the other way. So we'll have found our corner. But we can do the same thing for Tor. So for Tor prime. So Tor prime orients T to the left, and I claim that it also orients S upwards. Why is that? Well, because otherwise S would distinguish Tor and Tor prime, right? Tor orients S upwards by choice, by definition. If Tor prime oriented S downwards, then S would distinguish Tor and Tor prime, so little s would be in AJ, but it isn't. Right? Why would it be in AJ? Well, if it distinguished them, it would distinguish them efficiently by this. So Tor prime agrees with Tor on S. And now we can do the same thing with this corner. Here, C prime. And we get the same contradiction as here if C prime has order at most T. So C and C prime have order bigger than order T. But now we're done, because now we consider these two bottom corners here. So D prime and D. And they have now order less than S by submodularity. Right, so this corner has order bigger than T, so this must have order less than S, because the sums are at most the sums of orders S and T. And likewise, this corner has order bigger than t, so this has order less order s. But now let's look at what sigma does. Sigma orients S upwards. So by consistency, it must also orient these yellow corners upwards. They can't, it has to orient them, and they can't point away from each other by consistency. But now, sigma prime cannot orient them any differently from S, because then the corner it orients differently from S would distinguish sigma and sigma prime, and it would do so super efficiently because it has order less than the efficient distinguisher. So S prime also orients them up there, and also S prime. But now we have a proper a contradiction to the robustness of S sigma prime, because sigma prime orients S down and these corners up, and that's a contradiction to robustness. And that's it. 30 minutes. Thank you for your patience.